As described before, we use a specific equation of the resistance to make a specific sensor, specific resistive sensor. We call it strength gauge. Another type of displacement measuring system, measuring sensors, is inductive sensor. And like the resistive sensor, we need an equation. A specific equation should be used to make a to build a exact and predictable sensor. As we know, the value of the inductance L can be measured by this equation. N power 2 multiply geometric form factor and effective permeability of the medium mu. All these parameters can be used to fabricate a sensor based on inductive sensor. But changing the number of turns of coil is not available, not an available method. But geometric form factor and effective permeability of the medium is two parameters which are available to build a good sensor. Based on primarily geometric form factor, we can fabricate three types of inductive sensor. The first one is a self-inductance, the second one is the mutual inductance, and the third one is the differential transformer. We call it LVDT. And we start inductive displacement sensor from self-inductance. As we see, self-inductance is about a coil. Self means one coil. As you can see, we have one coil here in these two schematic. The first one, we have a separated coil, two parts of one coil, part 1 and part 2, and the geometric form factor of this coil will be changed by movement of these two parts of coil. If these two parts is close together, the geometric form factor of this coil will be increased, and when these two parts of the coil is far from together, the geometric form factor of this inductance will be decreased. Also, changing the geometric form factor with movement of a magnetic core within the coil. If the magnetic core is outside of the coil, the geometric form factor will be decreased, and when all of the magnetic core is inside the coil, the geometric form factor will be increased. The change in inductance for this device is not linearly related to displacement, as you know, and these devices have low power requirement and produce large variation in inductance makes them attractive for radio telemetry application, especially in medicine applications. These are good and cheap, but linearity problems uh, need some extra driver, extra circuits to overcome the nonlinearity of the output of these types of sensors. The second type was mutual inductance. Mutual means that we have two sensors with one source to excite the primary coil, and we need to induce the second coil with the magnetic field between these two coils, primary and secondary. We apply a voltage on A and B, and we now can read voltage from C and D terminals, and the space between these two coils will affect the output voltage on VCD. If these two coils is close together, the voltage will be increased, and vice versa. Also, we can fix the coils. But we can use a magnetic core within these two coils if this magnetic core share equally between these two coils, primary and secondary. We have maximum induction between two coils, but if the magnetic core is placed only inside one coil, for example the first one, or inside the second one, the induction will be reduced. We can use these types of inductive sensor to measure cardiac dimension and monitoring infant respiration and other types of measuring like arterial diameter measuring. And also we can measure some diameter, some change in the size of some organs like kidney and like some blood vessels, left ventricle, and so on. As you can read, the induced voltage in the secondary coil is a function of the geometry of the coil, and the number of primary and secondary also turns is another important feature, and the frequency and amplitude of the excitation voltage also is important. The induced voltage in the secondary coil is a nonlinear function of the separation of the coil. In order to maximize the output signal, a frequency is selected that causes the secondary coil to be in resonance, and the output voltage is detected with standard demodulator and amplifier circuit. But the last and the most important inductive sensor is linear variable differential transformer. We call it LVDT, one of the widely used sensor in physiological research and clinical medicine. We use it to measure pressure, displacement, and force also. And in this type of sensor, we have three coils composed of a primary. This is a primary coil, terminals A and B, and two secondary coils are connected in a position in order to achieve a wider range of linearity. It is because of the nonlinearity rejection using two opposite coil structure. The primary coil will excite two secondary S1 and S2, and the output voltage of these two secondary will be add with together, but because of the polarity of these two coils, the output will be zero if the magnetic core is placed at the middle of S1 and S2. And if this core is close to only S1, the output voltage of S1 will be higher than S2, then the output voltage will be with the similar polarity and phase of voltage P. And if the core is close to S2, the output voltage of S2 will be higher than S1. Therefore, the output voltage at the terminals C and D will be with the phase inverse of the phase of P1. We will talk more in the next slide. The primary coil is excited with frequency of 60 Hertz, between 60 Hertz and 220 kilohertz, and a change of phase by 180 degree when the core passes through the center position and saturation on the ends. These are two important features of the output of this LVDT inductive sensor. We have two coils at the secondary part, and based on the structure we have a input signal with this phase, and the output of the sensor 1 is something like that, and the output of sensor 2 is something like this. If we place the core at the center, these two signals are equal and therefore the output will be 0. This signal will add with this one and the output will be 0. But if the sensor if the core located here, if the core is located here, the output of the secondary one is high and the output of secondary 2 is low, as I told you before, and adding these two signals together leads to a signal something like this. As you can see, the phase angle of the output with the input is similar. And if we move the core to the bottom or close to S2, the output of S2 will be increased and the output of S1 will be decreased. Therefore, adding these two signals will leads to an output like this. And as you can see, the polarity or the phase angle of the output is 118 or reverse phase angle. Positive, negative, positive, negative, and negative, positive. Based on this description, you can see if we have these two situations, situation 1 and situation 2. Situation 1 is a specific form of displacement from positive position. Positive position means here to negative means here, moving the core from up to bottom. As you can see, we move from up to bottom to negative. And situation 2 is about moving the core from positive position and going to 0 position. 0 means the center. Center is here. And come back to positive position. As you can see in the situation 1, in condition 1, using condition is better than situation. In condition 1, we have a strong output from the position of the beginning and the large output, as you can see here, a large output here. And this is the signal of the excitation. As you can see, the phase angle of the primary coil and the output voltage is equal by here, and after this point the phase angle will be changed. The phase angle here is 118 degrees. As you can see here, positive, but here is negative. here negative, but here is positive. The phase angle of excitation, the difference between the phase angle of the output and input is 118 degree. It means that zero crossing, here is the center or zero position. Zero crossing leads to phase shifting. But if we start from positive, reach to zero, and come back to positive positions, as you can see, will occur without any phase shifting. This curve is for primary excitation signal, and the black one is for the output of LVDT. And as you can see, the phase angle between the output and the input primary signal is zero. Therefore, we should be able to discriminate between these two conditions. As you can see, we have two conditions here with same voltage but with different phase angle, and we should be able to discriminate these two conditions, and only solution to discriminate these conditions is using a phase sensitive demodulator as the modulating stage. An ordinary rectifier demodulator cannot distinguish between these two same value of variation but different phase angles. We need to use a phase sensitive demodulator for distinguish between these two conditions.